It's time to experience something glorious. Unacademy Combat. Compete, crack, conquer.
A challenging GATE contest engineered to give you an experience like none other, where you put your knowledge to test
and battle it out with a test
to bring out the best in you. Unacademy Combat is the most competitive, gamified contest for GATE till date, with the best of the questions by best educators.
With detailed video solutions from top educators right after each contest.
Combat live with peers to get real-time rankings and win big.
Participate in every contest to improve your ratings.
Challenging contests every fortnight or alternate Sunday. Live ranking after every question. Big rewards for top rankers. Your passion to crack GATE deserves this. Your hard work towards your dream deserves this. Fuel your inner fire for the ultimate GATE challenge. Unacademy Combat. Register now.
Welcome to Unacademy and welcome to Control Systems Revision, quick revision of Semester Exams, Chapter 4, second part, Lecture 7. Welcome Karthik, welcome NKC, welcome Shivakumar Chandrakiran, welcome to Unacademy. Good to see you. About me, I am sravan Kumar, having 7+ years of teaching experience and mentored more than 5K students for GATE and engineering services and also cracked GATE. You can use my code YSK10 to get the discount on your Unacademy subscription for a limited period of time. Unacademy, let's crack it. Crack GATE and ESE with India's largest learning platform and get subscription as early as possible. You can also install Unacademy Learning app from the Google Play Store and get subscription to Unacademy. Once you install, what you get is daily live classes, structured courses, live test and quizzes, and unlimited access as well. As a part of Iconic subscription, you'll have a personal coach, study tracker, mains question and answer, and all the benefits of Plus. In Plus subscription, you have daily live classes, structured courses, live test and quizzes, and unlimited access as well. You can learn from the top educators of the Unacademy, as you see. Raghavendra, good evening. Welcome to Unacademy. You also have GATE and ESE year-long batches and courses for all the subjects and all the courses. In Iconic subscription, you have all the benefits of the Plus subscription along with personal coach, personalized test analysis, study planner, preparatory study material, and many more. If you are opting for Plus subscription, you can use my code YSK10 to get the maximum discount on 24-month subscription, and this is also for a limited period of time. I suggest you to go for the Iconic subscription for 12 or 24 months. And you can use my code YSK10 to get the maximum discount for a limited period of time, as the plans are about to change in a very short period of time. So now, as a part of this session, we'll deal with the Chapter 4 root locus method of design and also Bode plot method of design. This is purely of designing. We'll solve some problems. First, let me explain you about a compensator. Any control systems, the aim of a control system is to have a specific objective. It has some specific objective. A very good control systems or a perfect control systems will give you less error or accuracy, good accuracy, or good speed of a response. But unfortunately, what happens is this is not always possible to get all the desired specifications. So what you do is you adjust the gain to get some, you adjust this gain to get the desired performance. But this gain will give you good steady state error or minimum steady state error, but it will affect the transient state. It will affect the transient response of the system. So this method is of adjusting the gain is not always feasible. So what we do is we insert a device or an equipment in control systems to get the desired performance or characteristics, and that piece of device that is inserted is called as a compensator. We call it as a compensator. That is, we redesign the system. Here we redesign the system by adding a device called as compensator. Why do we do this? To get desired performance or desired characteristics. Supraja, good evening. So these are some of the points related to the compensator, and based on the type of compensation, the compensators can be classified into three types. One is series, how a compensator or a device is inserted, series compensator or a parallel compensator or a series parallel compensator. Let's say you have G of S, a plant, and if you insert a device before this as GC of S, we call it as a compensator. So this, if this is inserted in cascade or series to this G of S, this is called as the series compensator. Now if you add this in parallel to this G of S, if you add this GC of S, you call it as a parallel compensator. Now if you are adding both in series and parallel, if you use both the combinations, we call it as a series parallel compensator. We call it as a series parallel compensator, right? So this is series parallel compensator, and as I told you, we also have something like lag compensator or lag network. We call it as a lag network, or we also have a lead compensator, the other type of classifications based on the circuit, or a lead network, and combination of these two is lag lead. The third one is lag lead compensator, which has both the characteristics of lag lead network. Soumya Narayan, good evening. Welcome to Unacademy and welcome to Control Systems course. Now if you see a lead compensator, a General Electric, and these compensators can be electrical or mechanical or anything. That means the device that is inserted can be of electrical one or mechanical one or whatever it is. You can take different types, pneumatic or hydraulic. They can be of any type. Now we are considering electrical network or lead compensator or lead network. So it is a resistor with a capacitor. We'll have a derivation because this is a quick revision. I don't want to just give you that. So this is E1, E2, C, R1, R2. If you find this ratio of the transfer function of this network, you'll get a lead compensator basically. And for a lag compensator, you have a network like this. You have a resistor, and if you place a capacitor in series with a resistor and find the output across this resistor and capacitor E2, and if this is E1, R1, R2, we'll derive this lag compensator transfer function and lead compensator transfer function from these two networks. And if you combine these two and just design a network, that is a lead lag compensator or lag lead compensator. So you need to know what is a lead compensator transfer function and what is a lag compensator transfer function. So let's write it for first one, lead compensator. So it is for a lead compensator, you'll write it as G of S is equal to S plus 1 by T by S plus 1 by alpha T, and this is S plus 1 by T by S plus 1 by beta T. Alpha is the lead angle and beta is the lag angle. This is for a lag network. And in problems, what we do, there is a procedure to all these problems, either a lead compensator or a lag compensator or anything, lead lag compensator. There is a separate procedure that need to be followed, but I'll tell you the general procedure that any question. So you'll be given a question, because we have to solve, we are in a question and answer series revision. Let's say you are given a question, k into s plus 1 into s by s into, let's say it is s into s plus 3. What we do as a part of this compensation is, and he'll give you some desired specifications. The desired specifications can be time domain or frequency domain. If you are giving us let's say maximum peak overshoot is 20% and kV, velocity error constant, should be 10. If this is specified, we'll generally go for the root locus technique. If gain margin, phase margin is specified, we'll go for the Bode plot technique, because they are frequency domain techniques. These are time domain techniques. So in this, what we do is, first, for the first step that you have to do is, you need to draw the root locus for this network, root locus, and we call this first transfer function as an, or system as an uncompensated system. This is an uncompensated system. Then what we do is, we'll find dominant poles. I'll tell you what are those dominant poles and how do you find them. Based on the given values of MP and KV, we'll find the dominant poles. And after finding those dominant poles, you need to determine GC of S. What is that? Compensator network. That is either lead or lag based on the question, S plus 1 by alpha T. You need to first find alpha value, T value, then you need to substitute in this. Then what you have to do is, you'll connect this GC of S in series with G of S, right? And you'll combine these two. Total G dash of S is equal to GC of S cascade into G of S. You'll get a new network. Let us say GC of S is something S plus 0.2 by S plus 0.5. So what you have to do is, we got GC of S, so we'll take S plus 0.2 by S plus 0.5 into G of S that we have taken, that is S plus 1 by S into S plus 3. So this transfer function becomes compensated system, right? We are adding a compensator and finding the transfer function G dash of S. To this, actually you need to draw the root locus. To this transfer function you need to draw the root locus actually, but instead of doing that, you can also verify in other way, right? In other way, what you can do is, instead of drawing this root locus, you have MP as 20% and KV as 10%. For this transfer function, compensated transfer function that you get, find MP and KV, and if it meets the specifications, if you find MP and KV for the uncompensated network, if it meets these points, let's say MP is, he'll not give you exact 20% or 10%, he'll say greater than 10 or something. If it meets these specifications, then our design is perfect. So the same thing you'll do in the Bode plot also. The only difference is, let's say you have a question like G of S is equal to K into S plus 1 by S into S plus 3. What you do is, to this you'll find the Bode plot. You'll first draw the Bode plot and also find k value for the given. He'll also specify velocity or acceleration error constant as well as gain margin and phase margin. Gain margin or phase margin. So you'll find this k. You'll plot this Bode plot. To this, if a lag compensator is asked or a lead compensator, or we will solve lag and lead compensator in this particular session, we'll find alpha, beta, t values and substitute in the GC of S. We'll substitute in GC of S. So once you get these GC of S and G of S, we will again find the transfer function GC of S and G of S. How do you find GC of S? That depends upon a procedure here in between these two. Once you plot Bode plot, you will get a gain margin, right? We will get some gain margin, but it should be, let's say this is 35 degrees and we got some 15 degrees. We'll find some new gain margin based on some calculation steps. Then based on this gamma value, you'll find alpha, beta and t. Then you substitute in this GC of S. Then you get this transfer function GC of S. And to this is called as a compensated one. This is a compensated system and this is an uncompensated system. The given system, generally the question that is given is an uncompensated. You should draw a Bode plot to that uncompensated system and you need to add a compensator. You need to add a compensator GC of S. You'll have that formula as I told you, S plus 1 by t into, if it is a lead lag compensator, I'll tell you, if it is a lead lag compensator, you'll write like this: S plus 1 by t1, S plus 1 by alpha t1, S plus 1 by t2, S plus 1 by beta t2. This is what you'll find. You'll add this to this GC. GC is added to this G of S. Now this will become a new compensated system. And to this, you need to draw the Bode plot actually. Right, but instead of drawing Bode plot, you can also verify KV for the given question, or gamma you can find it directly by mathematical calculations instead of drawing Bode plot to verify our compensation is correct. You'll easily understand this once we are solving a problem. I'll just take up one question from Nagurkani so that you'll be easily understand. These techniques you'll understand only if you are able to, if you solve a question, right? So I'll just take up one question from Nagurkani. The question says, yeah, this is a question. So I'm just taking one question. The question is, the forward path function of a certain unity feedback system. The forward path. Yeah, I request you all to tell your friends Karthik Jilla, Shivakumar, Chandrakiran, Raghavendra, Supraja, Soumya, inform your friends to join the session. This is one of the important questions for your semester exams. One definite question of 15 marks will be, or the final full marks will be given to you in the external exams. Either the procedure or a problem. Most of the times a problem is asked to design a compensator if you can check your question papers, semester exams. The forward path transfer function of a certain unity feedback system is given by G of S is equal to, the given transfer function is K by S into S plus 2 into S plus 8. He is asking us to design a lag compensator. Design a lag compensator, suitable lag compensator, so that the system meets the, inform your friends to join the session following specifications. Inform everyone to join the session. Just we are going to start a problem. I'll wait for 5 more minutes. The first specification is percentage overshoot is less than or equal to 16%. Second specification is, the question here also is specified for unit step input. If you are not able to see, just listen, it is for unit step input. And second one is steady state error less than or equal to 0.125 per unit ramp input. Per unit ramp input. This is the question. So read the question carefully. Let's read the question once again. the forward path transfer function, that is open loop transfer function simply, of a certain unity feedback system. Feedback is unity, so h of s you can directly write it as 1 is given by g of s is given. Design lag compensator, and he has not specified whether to use a root locus technique or a body plot technique. But looking at this, the percentage overshoot, if you see, let's read the question once again first completely. So design a lag compensator so that the system meets the following specifications. What are the specifications? First one is maximum peak overshoot, that is percentile MP should be less than 16%, and steady state error ESS is less than or equal to 0.15. This should be, if you design a compensator and add it to the system, the percentile overshoot should not be greater than less than 16%, should be less than 16%, it should not be greater than 16%, and steady state error must be 0.125, right? So this should be the condition. So just check the question once again. If you want, you can also write the question. Right? Is this fine? No, let's go. So in solution, first thing that you have to write is write g of s. What is the g of s that is given? K by s into s plus 2 into s plus 8. That's the first step. Now second step, what you have to do is write which compensator. Sometimes he may specify, sometimes he may not specify, so you have to write lag compensator here. This is lag compensator. For a lag compensator, what are the values that you find? Just look at the transfer function of lag compensator. 1 plus 1 by s plus 1 by t by s plus 1 by beta t. So this is gc of s is equal to s plus 1 by t by s plus 1 by beta t. So you will observe that you need to find the value of t and beta so that you can write this gc of s. Right? This is clear. Now Puram Meghana, welcome, good evening Meghana, inform your friends. Now third step, you need to draw root locus. You need to draw root locus for this k by s into s plus 2 into s plus 8. So we'll just directly take up how do you do this. I'll just tell you. See, I'll just roughly tell you how do we do this, but we have to find it exactly. But let's see. Now, what is the first step that you do in this root locus? We'll write it very short. So first we'll write number of poles 3, number of zeros 0. Then you can write p minus z directly, that is 3. What is this 3? Number of asymptotes. So if you know this number of asymptotes, you can write theta 1 is 60 degrees, theta 2 is 180 degrees, theta 3 is 300 degrees. I guess you know this. Vijay Kumar, good evening. Right, and you need to find centroid. Centroid is equal to 0 minus 2 minus 8 minus 10 by 3, so it is minus 3.3, I guess. So asymptote centroid minus 3.3, right? Now at, let's say this is minus 1 minus 2 minus 3 j1 j2, because this is j omega axis, this is real axis. 1 2 3 minus j1 minus j2 minus j3. So where are the poles? Poles are at origin minus 2 and minus 8. Oh, we did not take minus 8. Let's take minus 8 also. Let's take, just try to extend it. I'll just try to extend this. And let's say we have a minus 8 at this point. So let's say this is minus 8. This is minus 8. So this is minus 8. Now where does the root locus exist? As you know, root locus will exist between these two. Root locus will exist between these two. Yes, you know that. And root locus also exists this side, right? You know that. And because there are two poles adjacent to each other, there will be a breakaway point. And how do you determine that breakaway point? So you need to write it very clearly, but I'm just trying to write this because root locus we have already discussed. 1 plus g of s into h of s is equal to 0. That is s into s plus 2 into s plus 8 plus k is equal to 0. And k is equal to minus s into s plus 2 into s plus 8. So you need to differentiate it. Should I write it in the separate page? So you'll find breakaway point 1 plus g of s into h of s is equal to 0. Raju, good evening. So that is k is equal to, you'll get minus s into s plus 2 into s plus 8. Differentiate this, dk by ds is equal to 0. I'll think you'll get s is equal to, I'm just trying to write these values directly. You'll get this as minus s cube plus 10s square plus 16s. So get s is equal to minus 0.9 and minus 5.7. Right, so these two are the values that you get. Of this, for 0.9 it is valid because you can see 0.9 is between this, minus 0.9 is between these two, right? So this will be the breakaway point. So can I write this as breakaway point here? Yes. So root locus will travel to this point, root locus will travel to this point, and from here it will break. But you need to draw the asymptotes. Where do you need to draw the asymptotes? At minus 3.3. Let's say this is the point minus 3.33, which is the centroid. What is this? This is the centroid. At this point you need to draw the asymptotes with 60 degrees. What are the asymptotic angles? 60, 180 and 300, right? Yeah, 60, 180 and 300. So let's say these are the points. Yeah, these are the asymptotes. These are asymptotes of 60, 180 degrees and 300 degrees, right? Now, and what will happen to this? This will, root locus will travel like this now. So this is how root locus will travel, either like this or like this. So this is the and you also need to find these points. You can also find these points. What is that? I use RS criteria. You can also use some other methods to do that. So let me tell how do you what do you get there. So you have s cube plus 10s square plus 16s plus k is equal to 0. Substitute s is equal to j omega in this. You get j omega whole cube plus 10 into j omega square. Nikhil Chakravarti, good evening. Plus 16 into j omega plus k is equal to 0. And on equating imaginary part, equate imaginary part equal to 0. This is another method. Equate imaginary part is equal to 0. You get minus j omega cube plus 16 j omega is equal to 0. So you'll get omega is equal to plus or minus 4. This is what is important. Omega is equal to plus or minus 4 radian per second. So these values will be the point here. This is plus j4 and this point is minus. I've just drawn it down, but it must be up, I guess. Yeah, you can just remove this. I'll try to draw it above that because it is plus j4 and minus j4, and it should be above this because j3 is here, right? This is j3. So j4 is somewhere here, so it should travel from these points. So it should travel, it can also go above this, don't worry. It can also go, it is breaking at this point minus 0.9, and it can also go above this asymptote. Don't worry about it. It can also travel above asymptote, but it should travel along this asymptote towards infinity, right? So this is root locus. Now this is fine till this point, you know well, because we need to draw the root locus. Now what are the specifications that are given? So let me do that. Yeah. What are the specifications that are given? We should write it. Specifications. One specification is percentile MP should be less than or equal to 16%, and steady state error, this is for unit step and this is unit ramp, it should be the question is that should be less than or equal to, right? That's also less than or equal to, it should also be less than or equal to 1.25. Now how do you find this? What do you need to do here is you need to find dominant poles. What are dominant poles is you can find this from this which are you can say that which are very close to the imaginary axis. You can find this from this MP. What is percentile? MP is equal to, we already know, e power minus pi zeta by under root of 1 minus zeta square. What is this value? Percentile MP is 16%. What is 16%? 0.16 e power minus pi zeta by under root of 1 minus zeta square. Can I write minus pi zeta by root over 1 minus zeta square is equal to ln 0.16? Yes, you can write. So what is minus? From this you can just write the value of zeta. Find the value of zeta. So you'll get zeta is equal to, if you want me to do that, minus pi zeta by root over 1 minus zeta square is equal to ln value of 0.16 is minus 1.83, right? Now squaring on both sides, square on both sides, so you get pi square zeta square by 1 minus zeta square is equal to 1.83 square 3.34. So you can write pi square zeta square is equal to 3.34 into 1 minus zeta square. Try to simplify this. Pi square zeta square is equal to 3.34 minus 3.34 zeta square. Yes? No. Can we do this like this? You can write this as zeta square pi square plus 3.34 zeta square is equal to 3.34. It is 3.34. So from this, if you find zeta, zeta will be equal to, just check it out, it is 0.5. Zeta is equal to 0.5. So you need to find dominant poles. For that, first you need to find zeta value, damping ratio. Now once you know this damping ratio, theta, you need to find angle, that is cos inverse zeta. So cos inverse 0.5 will give you, cos inverse 0.5 will give you, cos inverse 0.5 will give you 60 degrees. This is 60 degrees, cos inverse 0.5. Now what you have to do with this 60 degrees? Just you need to go to this, you need to go to this root locus. You need to go to this root locus, and with respect to this real axis, draw a line with 60 degrees. Draw a line with 60 degrees like this. Now it will intersect this root locus at a particular point. This will intersect root locus at a particular point. Now find out this point. If you draw out the root locus exactly, you'll know this imaginary value, you'll know, and this real value you'll know, right? You can find this real and imaginary value, and this will be the coordinate of that. So that coordinate will be, that coordinate will be something like this. This is ST, we'll call it as dominant pole, minus 0.75 plus J 6.35. This is the dominant pole. This is the dominant pole. And you need to, next step is you need to find gain. We need to find gain at SD. And how do you do that is, let's say you have a dominant pole here and you have rest of the poles here. You need to find the vector lengths from here. Let's say the scale is 0.5. Scale is 1 centimeter is equal to 0.5. And if you get this as 2 units and this as 2.6, in this particular problem you'll get that, and this is 14.7, or let's say this is, you get it as 3 and 14.7. Let's say this is 3 units, 3 units. So you'll find length. This is L1 length, this is L2 length, this is L3 length. So L1 is equal to 3 into 0.5, that will be 1.5. Similarly L2 is equal to 3 into 0. Sorry, this is 3.6. You'll get it 3.6 because it can't be same. It will be different for one pole and the other pole, the distance, right? So this is 3.6 into 0.5. You get it as 1.8, and L3 will be 14.7 into 0.5. You'll get it as 7.35. So how do you find this K value? Gain at SD. K is equal to product of lengths from poles by product of lengths from zeros. If you do not have zeros in a given question, this product of lengths will be taken as 1. So what is K value now? It is 1.5 into 1.8 into 7.35 by 1. So you'll get K value as 19.84. You got the K value as 19.84. So K is equal to 19.84. But we are already given this K value. See here, for velocity error constant, steady state error is 0.125. So ESS must be less than or equal to 0.125. That is the question that is given. So, and it is a ramp input. So let us find velocity error constant. Limit s tends to 0, s into g of s into h of s. You know this, right? So limit s tends to 0, s into, what is g of s into h of s we got? It is this K value. What is K value? 19.84. So this is K by, actually this is K by s into s plus 2 into s plus 8. So limit s tends to 0, s into K value is 19.84. You can approximate it to 20. 20 by s into s plus 2 into s plus 8. You can cancel this and apply limit. You will get 20 by 2 into 8 will be 1.25. So K value is 1.25 that we got. K velocity. Right? So we already got K is equal to 19 point that we have used in this. So KB is 1.25. What is ESS that is given? 1 by KB we know. What is 1 by KB? 1 by 1.25 will be 8. So this is 0. You know this KB value. KB we got it as 1.25. Just listen. 1.25. KB is equal to 1.25. What is steady state error? ESS is equal to 1 by KB. From this you can write KB is equal to 1 by ESS, or 1 by ESS is 0.125 from the given question. You can see this is 0.125. So you will get KB is equal to, this is KB actual, this is KB desired, this is desired, this is actual that we got. So KB is equal to 1 by 0.125 will be 8. So KB is equal to 8. Now this is actually 1.25 is the actual K gain, and this is the desired one. So we need to improve that K. So A is equal to K by K, that is K desired by K actual. K desired is 8 by K actual is 1.25, so it is 6.4. So the value of A is 6.4. It is A is the factor by which K need to be improved. Right? So we got the value of A. A is equal to 6.4. Now from this you can find beta. Beta, as you know, transfer function GC of S is equal to s plus 1 by t by s plus 1 by beta t. So beta is a value, beta is at least 10 to 20% of A. Beta must be 10 to 20% of A. So you can take beta is equal to 1.2, 10% or 12% of A. So 1.2 into A value is 6.4. So you'll get beta is equal to 7.68. Beta is equal to 7.68. Now you need to find t value. Now t is equal to 1 by location of 0. 1 by location of 0. This is another condition. So location of 0 is nothing but 0.1 times. We'll assume that location of 0 is 0.1 times of second pole of g of s. Second pole of g of s. What is the second pole that we know? It is 2. Right? Minus 2 actually. So it is minus 0.2. So t is 1 by zc. So that is 1 by 0.2 will be 5. So t value will be 5. So we have found beta and t value. Can I write gc of s? Gc of s is equal to s plus 1 by t by s plus 1 by beta t. So you'll get s plus 0.2 by s plus 0.026. Just find this 1 by t and 1 by beta t. Now the transfer function of compensated system is transfer function of compensated system gc of s into g of s, and this is the closed loop system, you can see. Right? Now you need to write this. This is plus, this is minus. Now you need to write that gc of s and g of s. What is gc of s? S plus 0.26, sorry 0.2 by s plus 0.026, and this is 20 by s into s plus 2 into s plus 8. So the transfer function of compensated system is s plus 0.2 by s plus 0.026 into 20 by s into s plus 2 into s plus 8. So this is the desired transfer function to get MP of 16% and less than or equal to, and ESS less than or equal to 0.125. So to this you can find MP and ESS which will satisfy these two requirements. Right? So this is how we will do that. So let's see that once again. You can listen to this once again. So this is the root locus technique of designing a compensator. So you need to draw the root locus first. From that you need to find the centroid and everything. Then based on the specifications value you need to determine dominant poles. From that you will find zeta value. You will get a zeta and you need to find theta and draw a line that will intersect this root locus at a particular point, and you need to specify that point as SD. This is dominant pole. SD is dominant pole, and you need to find gain at this SD. K. You need to find this K. If you the product of lengths of lengths from the poles to the product of lengths from the zeros. Then if once you find this K value, you can approximate it this to some round figure. Then you are also given the second. You'll get this zeta from the first specification. You'll get this zeta from this first specification MP, and you'll find from the second specification you can find the value of kV, because we got a gain as 20 and the kV value, velocity error constant, will be 1.25 for this dominant pole, for the dominant pole that you got. And you'll find ESS, that is desired. This is the actual ESS that we got, and this is the desired ESS that you get. For the desired ESS you will get the desired kV value, velocity error constant, and you need to find the factor by which the K has to be improved. So A is the factor by which K will be increased, that is KD by KA, desired K by actual K. So 6.4. From that you can find beta. Beta is always 10 to 20% of A value, or you can take it as 1.2 into A. So you'll get 1.2 into A, you'll get the value as 7.68. So once you get the value of beta, the other value that you need to find is T. T is actually, you'll write ZC is equal to minus 1 by T. This is the actual formula, but I have directly written T is equal to 1 by minus ZC. Minus of minus, that will be plus. So ZC is equal to 0. It is 10% of second pole. It is a 10% of second pole value. That is, you are bringing that 0 to the closer to the imaginary axis. 10%, that is 0.1 into second. So you'll get minus 0.2. If you substitute, you'll get 5. So T value is 5. When you know beta and T, you can just directly substitute in this. You'll get the compensated transfer function. So when you substitute, you'll get a full transfer function with compensator and a plant. So this is the compensated network transfer function. Hope you have understood this, and in this, as a part of this, we have learned root locus design by using root locus technique as control systems chapter 4. We'll see Bode plot technique in the other session if possible, and then we'll continue with the next part, unit 5, quick revision. As I always tell you, we have #1 study channels on Unacademy, and also do like this video, share this video, and also comment and inform your friends to join the sessions. You can use my code YSK10 to get the maximum discount, and click on this bell icon to get notification of my classes, and you can join the Telegram group for upcoming videos. Do subscribe to Unacademy and Unacademy Semester Exams. Like this video, share this video. This is one of the important questions for your external examination semester exams. So let's crack GATE and ESE with India's largest e-learning platform, Unacademy. Thank you so much for joining me today on this session.